It is a pleasure that I introduce our speaker today, Dr. Robert Delaney from Boston University. And he did his undergrad. Again, if I try to introduce him, I can take the entire 1 hour. So I'm going to take a couple of important pointers and split up between morning and afternoon talks. So he did his undergrad from College of Holy Cross and PhD from University of California, Berkeley. He taught at Northwestern and Tufts and moved to Boston University in 1980. And his main areas of interest are discrete dynamical systems and complex analytic dynamical systems. Though I didn't get the opportunity to read his textbook, all of my friends in India, I think we followed his book, Introduction to Chaotic Dynamical Systems. That is the book we followed in all the universities there. So, and he authored more than 100 papers in his field and authored more than 14 books. So if you want to know anything about dynamical systems, he's the guy. So he won numerous teaching awards and peer research awards, and I just read a couple of them. And in 1994, he received Distinguished Teaching Award from Northwestern, and 1995, he received Deborah and Franklin Tepper Hymo Award for Distinguished University Teaching. In 1996, he got the Boston University Teaching Award, and in 2002, he got the NSF Foundation's Director's Award for Distinguished Teaching Scholars. And in 2012, he was named as a Fellow of the American Mathematical Society. And from 2013 to 15, those 2 years he served as the President of the Mathematical Association of America. And the cool fact is, he is the mathematical consultant for the Hollywood movie, the Kevin Spacey's The 21. So math is cool, guys. So if you want to be a math major, please consider that. You might be doing the same thing in future. So without further ado, I'll introduce our speaker, Dr. Robert L. Delaney.
Thank you very much. Oh.
Thank you so much.
Well, I wonder what this is.
I know you do collect coffee mugs, so hopefully one in there.
Okay, all right. I'm going home then. See ya. Well, thank you for having me here. Let's see, you know a little bit about me. Let's see if I can find out something about you. How many of you like mathematics? Okay, good. I came to the right place. Good. How many of you think mathematics is the most beautiful thing you've ever seen? Fewer. How many of you would rather do mathematics than anything else on earth? How many of you are liars? Actually, my goal today in these two talks is to convince you that your answers to all three of those questions should have been yes. Okay, because the mathematics we're seeing today is absolutely beautiful and incredibly interesting. And as you'll see, there'll be some applications of this. I won't spend much time, but this morning I want to talk about the chaos game. Turns out that several of my former students use the ideas behind the chaos game to actually go to Hollywood and make these animated films. In any event, let's do the math. Let's begin with the chaos game. How many people know the chaos game? Good, okay, well, here's the chaos game. I'm going to start with 3 points, corners of a triangle, a red point, green point, and a blue point. It's an iterative game, so I need a place to start, so I put a point someplace, doesn't matter where. And now it's a random game. So what I do is I take a die, a 6-sided die, and color 2 of the sides red, 2 of the sides green, and 2 of the sides blue. Okay, so let me simulate that here. Then I roll the die, and depending on what color comes up, I move that point half the distance to the appropriate vertex. Roll green, move halfway to green. Roll red, halfway to red. Blue, halfway to blue. Oh, sorry, we're in Ohio. Half, you don't know what that word means. How did I say? Half? Half, whatever. It's half for the rest of the day. Keep going. Roll blue again, halfway to blue. Okay, I do this about a dozen times, and then I start recording where this point moves. Roll green, go halfway to green, but keep the previous point. Roll red, halfway to red, keep the previous 2 points. Okay, red again, blue. And I do this 100,000 times, and then the lecture's over. Okay? The question is, what's the pattern that's going to result when I do this 100,000 times? Okay, if you haven't seen this before, most people have no idea what's going to happen. Most people think, well, maybe the dots will just be a big blob in the middle. Some people think it'll fill the whole triangle. Most people aren't prepared for what's actually going to happen. Let's speed up and roll 10 times, 10 more times, 10 more times, 50 times, 50 more times. Now you're beginning to see a pattern there. Right? We're missing a triangular region in the middle. There's a little white region there and there and there. Let me speed up and roll 10,000 times, meanwhile making the dots smaller so you can begin to see the pattern. And when I do 10,000 more times, out comes a surprise, not a random mess, a distinct geometric image, the so-called Sierpinski triangle. And the second surprise is, this is a fractal. I'll explain more what I mean by a fractal in a minute, but first, why do we get the Sierpinski triangle? Well, suppose we had started with a point right there. That was my initial point. Why is there no point in the Sierpinski triangle right there? Well, remember, I erased the first 10 or 12 points when I started rolling the die. So, roll the die. Roll green, go halfway to green. And look what's happened. I started inside the largest white vacant triangle. After one roll, I'm in the next smaller sized white vacant triangle. Had I rolled red, I would have moved to that smaller white vacant triangle and blue down to that one. And continue. Roll red, halfway to red, next smaller sized white vacant triangle. Blue, halfway to blue, even smaller white vacant triangle, blue again, even smaller empty triangle. When I do this 10 or a dozen times, I'm inside a triangle that's so small you can't see it because of the resolution of the screen. And then what happens is I start bouncing around this image known as the Sierpinski triangle. Okay, I mentioned a fractal. Okay, what is a fractal? Well, there's several different ideas behind fractals, including fractal dimension, which is a non-integer dimension that I won't get into. But basically, a fractal is a self-similar set. What do I mean by that? Well, look at this Sierpinski triangle. Everywhere you zoom, you see a smaller and smaller copy of the Sierpinski triangle. That's self-similarity. For example, if I were to magnify that region there, you'd see a copy of the Sierpinski triangle. Zoom in on that, another copy of the Sierpinski triangle. To the lower left region there, another, even smaller copy of the Sierpinski triangle. Let me show you that by magnifying that region. And what you see is the more I magnify, the more you see the exact same structure. I'm going to let this animation go for the next 45 minutes. Okay, don't worry, you'll all have triangular eyeballs, but you'll all be mathematicians. Well, maybe I'll stop there. In any event, that's a fractal, a self-similar set. Okay, well, now let me go live and play a few other chaos games. Okay, here's an applet on the web called Fractal Ena. It's actually written by a couple undergraduates for me. I've put the 3 points down, a green point, a red point, and a blue point. And when I play the game live, out comes again the Sierpinski triangle. Now, there was no reason why I had to put these vertices at the corners of an isosceles triangle. I could have put them at the corners of a right triangle. And when I play this game again, out comes the Sierpinski right triangle. Or if I put this third dot someplace, as long as the 3 vertices form a triangle, when I play this game, out comes the Sierpinski triangle. Now, here's the third surprise and the basis for all the applications of all of this. When you look at the output of a chaos game, as long as you have a keen eye for geometry, you can read off the rules of the game I played to make that image. For example, look at this Sierpinski triangle. What you basically see, the way I've colored it, is 3 self-similar pieces, okay? And that's the same as the number of vertices I started with. And if you look at each of these self-similar pieces, they're exactly 1/2 the size of the entire Sierpinski triangle. 1/2 in terms of length and in terms of height. and 1/2 was the number I used to move to the appropriate vertex. So the geometry of the output of this chaos game tell you the rules that we use to play it. Let's do a couple more. How about this one? I put down 6 points, corners of a hexagon. You may not see the yellow point there. Now I've changed what we call the compression ratio. The compression ratio here is 3. What that means is if I were here right in the middle and I rolled red, I wouldn't move half the distance to red as I did in the case of the Sierpinski triangle. Rather, I'll compress the distance by a factor of 3. I'll move so that the resulting distance to the vertex I called is 1/3 the original distance. If I were here and I called black, I wouldn't move halfway to black. Rather, I'd move so that the resulting distance is 1/3 the original distance. So let's play the chaos game with those rules. And again, you get the same 3 surprises. Okay, not a random mess, a distinct geometric image. Okay, again, a fractal. This is the Sierpinski hexagon. As you zoom in, you see copy and copy of the Sierpinski hexagon. And then thirdly, you can go backwards. Just by looking at the result of this chaos game, I can tell you the number of vertices and the compression ratio. You see basically 6 self-similar pieces, and if you measure them, each of them is exactly 1/3 the size of the original Sierpinski triangle. By the way, do you see another very famous fractal in this picture? Look at the boundaries of these white regions. Right? All the boundaries of these white regions are what's called the Koch snowflake curve, another very famous fractal. Lots of interesting geometry here. Okay, another example. Let's put down 5 points, corners of a pentagon. Again, I don't know if you can see the yellow point up there. And again, I've changed the compression ratio to be 2.7. So if I were here in the middle and I called the red vertex, I wouldn't move halfway to red. I wouldn't compress the distance by a factor of 3. Rather, I'd move so that the resulting distance is exactly 1 divided by 2.7 times the original distance. So let's play that chaos game. And again, we get the same 3 surprises. This time the fractal is the Sierpinski pentagon. You can see 5 self-similar pieces, same as the number of vertices. And if you measure each of these self-similar pieces, you'll see that they're exactly 1 divided by 2.7 times the size of the original Sierpinski pentagon. Okay, good. All right, well now let me ump the ante a bit and let me play a chaos game that includes rotations. So let's start again with 3 points, corners of a triangle. If I call the green point or the blue point, I do exactly as in the case of the Sierpinski triangle. I move half the distance toward those vertices. But if I call the red vertex, I first move half the distance to red and then rotate by 90 degrees. With me, if I'm down here and I call red, I go halfway to red and then rotate in that direction by 90 degrees. And here's the result of that chaos game. And again, with a keen eye for geometry, you can read off the rules that I played, right? Because basically you see 3 self-similar pieces, the way I colored it, same as the number of vertices. This green piece looks like it's just half the size of the original fractal. Same thing with the blue piece, exactly half the size of the original fractal. But what about this red piece here? Notice this red piece looks like the original fractal, half the size, only rotated by 90 degrees. Okay. And one more example. Let's play the chaos game where I now rotate 180 degrees around this red vertex. That is, if I'm here and I call red, I go half the distance to red, but then flip to the other side. And then what comes out is, again, a different fractal, but the same 3 surprises, not a random mess. Fractal object, and again, as long as you have a keen eye for geometry, you can tell the rules that I used. Because look at this fractal. It basically has 2 legs and a head, right? The legs are standing, have 2 legs and a head. They're standing upright, 2 legs and a head. But the head is standing on its head. Head is below the 2 legs, rotated by 180 degrees. Again, you can always read off those rules. Okay, everyone with me so far? All right, let's make sure of that. Here's a quiz. Okay, you've got to tell me how I made each of the following fractals. By that I mean you've got to tell me the number of vertices, the compression ratio, and the rotations, if any. Okay, first question, the fractal icicle. How many vertices here? Excuse me, I said, how many vertices here? 2. No, how many vertices here? 4. This is one of the most amazing theorems in all of mathematics. This is what people always say first. They say 2 or 4. And then they settle on the right answer, which is somewhere in between. Actually, I use 3 vertices here. Look at this fractal. Okay, on the left, look at that piece. Looks like it's about half the size of the original fractal. Looks like I put a vertex right there and compressed halfway toward it. And the same thing on the right. Put a vertex on the right, compress half the distance toward it. And then look in the middle. What did I do there? Looks like I put another vertex right in the middle, compressed halfway toward it, but then rotated by 90 degrees. So I actually used 3 vertices, 1 compression ratio, and 1 rotation. Okay. In fact, you could have used 4 here. Do you see 4 self-similar pieces? Right? There's 1 here. There's 1 there. There's also a self-similar piece right here and also down below. So I could have used 4 vertices, but then there'd be 2 different compression ratios. And then, more importantly, the vertex for this piece wouldn't be right at the top, as you might have expected. Rather, it's somewhere off the side and impossible to get it, to get the picture to come out as symmetric as it is. So you could have used 4 vertices, but that's much more difficult. Okay, another question. How many vertices here? Now nobody answers. Let's try to count. You think it's 1? You think it's 2? You think it's 500? Pretty clearly it's 3. All right, there's 1 self-similar piece there. Looks like the whole fractal, only half the size. But, again, this fractal has 2 legs and a head, but this one's upside down. I've rotated 180 degrees. And the same thing up top. Compression of ratio 2, rotation of 180 degrees, and the same thing on the right. So it looks like I used 3 vertices, compression ratio of 2, and a rotation of 180 degrees at each stage. Mentioned earlier the Koch snowflake curve. How did I create this? How many vertices here?
6.
Good try. Here, 6. 4 is right. Actually, 4. Right? Look right there. That's a small, self-similar copy of the Koch snowflake curve. Looks like I compressed toward the left, in fact, by a factor of 3. Right? If I had started here and compressed by a factor of 2, I just would have gone halfway. I've got to compress by a factor of 3 to get that piece there. So compression ratio of 3. And same thing on the right. And then there's 2 more self-similar pieces. Looks like I compressed the whole fractal by a factor of 3, but then rotate by 60 or minus 60 degrees to get those pieces. And one last one, just to make sure no one passes the quiz. How did I make that fractal? How many vertices? 3 is right. Compression ratio of 2. Well, you don't know, it might be 1.99 or 2.01, but it's a compression ratio of 2. Any rotations here? Yeah, but how much? In fact, what I did was put 3 vertices, compression ratio of 2, and in each case I rotated by 90 degrees. Let me show you that. Let me take this fractal, compress it, and rotate by 90 degrees simultaneously. And when I do, I get that lower right-hand piece of the fractal. Do that again. Compress and rotate by 90 degrees, and I get that self-similar piece. And now if you look, you see another self-similar piece right here, and a third self-similar piece there. Looks like 3 vertices, compression ratio of 2 each, with a rotation of 90 degrees. Okay, so now we know how to make one fractal image. Now what we can do is string a bunch of them together and make a fractal movie. So how did I make this fractal movie? You've got to tell me for each frame how many vertices, compression ratio, rotations, and then what I did to move from frame to frame. So here's the animation. What's going on here? If you look closely, if you zoom in, you see different things are happening in different places of these fractal images. So, how did I make that movie? How many vertices? 3 is right. Compression ratio of 2, just like with the Sierpinski triangle. Okay? What about this piece there? You see the 2 vertices, you see the 3 vertices, you see the compression ratio of 2, but what about rotations? Is there any rotation there? No, it looks like I take the whole fractal and just compress it half the distance to the top. No rotation. What about in those 2 pieces? Yeah, it looks like I compressed by a factor of 2 and rotated each one in the opposite direction. So it looks like I used 3 vertices, compression ratio of 2. I said to rotate by, say, 10 degrees at each frame around the lower vertices, and I told the computer to iterate 100,000 times each time. That's all the data I had to throw in to the computer to make that animation. Okay? Basically 7 bits of information. That's data compression. That's data compression in a big way, and that's another major application of all of this. Okay. All right, well, one of the things that we do at my university is we run what we call math field days, where, well, actually, we run what we call chaos clubs in the Boston public schools. Okay, we go in and we just show the students some interesting new things that are happening in mathematics. And one of the things I always do with the students is ask them to make a movie that's A, beautiful, and B, I can't figure out how they did it. So here's how they make their movies. Okay, let's make a movie. Whoop. Sorry. We make that by, I need the starting frame. So here's the starting frame. Let's start by making a movie where we start with the Sierpinski triangle. And now let's make a movie where at each frame we rotate by 10 degrees around that top vertex. Okay, so much so that by the final frame we've rotated 360 degrees. Say the final frame of this animation will rotate 360 degrees around that top vertex. What's the final frame going to look like? Should be exactly the same, right? If I go half the distance to red and rotate by 360 degrees, that's the same as not rotating at all. So let's make a movie where we rotate by 10 degrees at each stage around that top vertex. So I'll need 36 frames and then a 37th to get back where I started. Let's make a movie with 37 frames. Okay, I'm rolling the die 10 or 20,000 times at each stage. Think of doing this 20 or 30 years ago before the computer. All of this is mathematics that's happened thanks to the computer in the last 20 or 30 years. Okay, so here's that animation. Okay. There's actually a lot going on here. Look at the top self-similar piece of the top self-similar piece. Watch what happens to that. That's rotating twice as fast. And then look at the top self-similar piece of the top self-similar piece of the top self-similar piece. That small piece up there, that's rotating 4 times as we go around. There's a lot going on in this animation. Okay? And again, I used very little data to make it. Had to put in 3 vertices, 1 compression ratio, 1 rotation, and say roll the die 10 or 20,000 times. Okay, as I mentioned, we do these in the chaos clubs, and one of my favorite movie made by a student was one made by Jason. Jason said to do exactly what we just did, rotate by 10 degrees around that top vertex, but meanwhile let that top vertex descend so that it ends up in line with the other 2. So here's the final frame of Jason's movie, just a straight line. So let's make that animation with 37 frames. Okay, I'm rotating around that top vertex 10 degrees at each stage, but now you see that top vertex is slowly crawling down to be in line with the other 2. Hurry up. I have something running in the background, I think. Anyway, here's Jason's movie. Thud. He called it The Death of Sierpinski. Okay. Again, a lot of stuff goes on in this movie, but very little data produced it. Okay, and here's my all-time favorite, produced by Lisa. Here's Lisa's Starfish. Ohio, do people know what a starfish is? Well, here we go. Here's Lisa's movie. How did Lisa make this movie? What's going on here? Notice that there's a blue paw of this starfish right here, which is a self-similar copy of the whole starfish. It looks like Lisa put 1 vertex right there with a compression ratio that's pretty large. Looks like it's about 5. And now look at the red piece of the starfish. That's another self-similar copy of the whole picture. Looks like Lisa put another vertex right in the middle and then compressed toward it by just a little bit and rotated by some angle. It looks like Lisa used 2 vertices, 2 different compression ratios, and then she rotated around that central vertex. Well, let's see. Let's go back to Fractal Ena. It looks like Lisa put 1 vertex in the upper left, right about here, with a compression ratio that was large, it was about 5. And it looks like Lisa put a second vertex right in the middle with a compression ratio that was small. What would be a small compression ratio? What would be no compression? No compression would be 1. You just rotate. So small compression would be something like, well, maybe 1.04, 1.05. I forget what she used. Oh, sorry, that's not the... Let me get rid of that. Typed in the wrong place. There we are, right in the middle. Looks like she put in a compression ratio that was small of 1.05, and looks like she rotated around that vertex each frame of the film by some angle, say 35, 38, whatever. So it looks like that's what Lisa did to make that movie. Let's see. Whoop. That's what comes out. You see the paws of the starfish, but not the kneecaps or the brains. There's no points in the middle here. Why not? How would you get points in the middle? Well, if you were, say, out here, to get points in the middle, you'd have to roll that middle vertex. When you call that middle vertex, though, you just creep toward it just a little bit and rotate. So you'd have to call that middle vertex again. Inch toward it and rotate. Inch toward it and rotate. Inch toward it and rotate. You'd have to call that middle vertex over and over again in succession. But if you ever called the upper left vertex, boom, you compress toward it by a factor of 5 and you're way on the outside. So in order to get points in the middle here, we've got to arrange to call that middle vertex over and over again. But remember, this is a random game. Okay, so the odds are 50-50 of calling that middle vertex. So we've got to change the probability of calling that central vertex. So how do you think Lisa did that? There's no probability here. How do you think Lisa changed the probability of calling that central vertex? Well, what she did was just add a second point, a third point, fourth point, fifth point, sixth point in the middle, and now when you play this chaos game, you've got a much better chance of continuing on to the middle. And in fact, what Lisa did was add a 7th, 8th, 9th, 10th point there, and there you see one of the images from Lisa's starfish. And again, notice the data compression. We basically have two vertices. We have two different compression ratios. We had to rotate by 10 degrees, whatever, around that central vertex. We had to say pile a dozen vertices right in the middle, and we had to say roll the die 100,000 times for each thing. Again, very little data goes in to produce this image. That's data compression. That's something that really took off in Silicon Valley a number of years ago. Okay, how are we doing for time? Okay, well, here's another thing on the web. It's called the Chaos Game. This is actually a game. Okay, what I've given you is the Sierpinski triangle down to some level. Okay, and in green, I've given you a target. Okay? The goal of this game is to take the starting point, which is right here in red, and move it into the interior of the target. And how do you move this point? Well, you use the rules of the original Chaos game. For example, if I click on blue, I move half the distance to blue. This point moves here, almost there. I'm on the vertex of the target. Remember, I have to get into the interior. Maybe I should go green. No, I'm still on one of the vertices of the target. Go blue and green. Now I'm still on the boundary of the target. Pretty clearly, I've got to go up. And then maybe left, and left again, and then right. And I made it. I'm into the interior of that target. I won. Well, not quite. I don't know if you can see it, but it took me 8 moves to get into the target here. The intergalactic world record for this chaos game is 4. I'm not very good at this. Anyone want to play me in the chaos game? If you beat me, I'll give you this computer. Oh, it's amazing. When we do this with the high school audience, 10,000 students storm up onto the stage. Nobody dares play me? I'm not very good. All right, finally. Come on up. Your name is?
Nicholas.
Nicholas.
Yeah.
You're from?
I'm from Cleveland.
Cleveland. Oh, Ohio, so you don't
Yes.
know what 1/2 was. Okay. Well, I'm a little bit worried. Let me change the rules a little bit.
Yay. We always get the love.
So, just have to click there.
Okay. Let's see.
Nicholas is going to go left. And then
It's really intense. Everyone's so quiet.
he's going to go
Go back.
right.
Us Clevelanders can never cut a break, can we?
Should become a Red Sox fan. Up.
Should I trust you? Yes. Up one more.
Very good.
Okay. I'll take
Very
6.
good. Very good.
Thank you. Thank you.
Oh, by the way, I forgot to tell you that if you don't beat me, I get to claim an article of your clothing. I
You
like
can have
this.
my right shoe. How about that?
Well, I'll take both of them, yeah. Look
Okay.
at that.
Okay.
Well, let's
Thank
see. It took Nicholas 11 moves to get in there. 6, no. 11. 1, 2, 3, 4, 5, 11, isn't it? I would have gone left and up, and then right, up, and right. 5. Sorry, Nicholas. There's an algorithm for getting into any one of these targets. Okay, no matter where I put this target, you can always figure out how to get in there in exactly 5 moves. But what's more important and more difficult is to figure out the algorithm that allows you to get into any given target, not just a specific one. Figuring out that algorithm is not that easy. But then what's more important is communicating that algorithm to other people. That's what's important. In fact, that's what mathematics is all about these days, figuring out the algorithm and then being able to communicate what's going on to other people. Once you figure out the algorithm, you can play this game at the hard level or at the master level. Okay, and at that level, you can always get into the target in exactly 7 moves. Okay, once you figure out the algorithm, I suggest you challenge your math professor to play you at this level, because at their age, they can't even see the target, right? So you're sure to win, okay? Actually, the target is right up there. And there's a way to get in there in exactly 7 moves. Okay. Well, I mentioned that several of my students had actually gone to Hollywood to use these ideas to make the backgrounds for certain animated films. Let me show you how that came about. Here's a slightly different kind of chaos game. Okay. For this chaos game, what I'm going to do is I'm going to start with a square. Okay? And then I'm going to give you 4 rules that tell you what to do with each point in the square. Okay, here's rule number 1. It says take the square, first squish it, more from the bottom than the top, and then rotate a little bit to the right. So, if we were playing this chaos game and I rolled 1 on the die, and my point were, say, up here in the upper left-hand corner, what I'd do is squish, and then rotate, and I'd end up at the corresponding point on the image rectangle. That's rule number 1. Here's rule number 2. Take the square and squish it. Okay? More from the sides than the top and bottom, and then rotate to the left. So if my point were again right here, and I said and I rolled number 2, I'd first squish and then rotate left and end up at the corresponding point on the image rectangle. Rule number 2. Here's rule number 3. Rule number 3 says first flip this square over its vertical axis and then squish and rotate right. So again, if I were here and called rule number 3, I'd first flip to the other side, then squish and rotate right. And I'd again end up at the corresponding point on the image rectangle. Finally, rule number 4 says take that square and squish it almost completely. Almost completely from the sides, not quite completely from the top and bottom. That's the final rule. Just to summarize, okay, rule number 1, squish more from the bottom, rotate a little bit. Rule number 2, squish, rotate left. Rule number 3, first flip, then squish and rotate. And then rule number 4, squish almost completely. So now let's go play the chaos game with those 4 rules. But first, here are the rules. Another different area of mathematics. Each one of these rules is given by a 2x2 matrix times a vector plus a translation vector. And just as with Lisa's starfish, each of these rules are applied with a certain probability. Okay, so all sorts of ideas in undergraduate mathematics come up in this area. Linear algebra, probability, geometry, etc. So let's go play the chaos game with those rules. And when I roll the die, out comes a surprise. Out comes a fractal, but not from Euclidean geometry, but from nature, the fractal fern. Okay, and if you look at the fern, as you zoom in, you see smaller and smaller copies of the fern. And that's true of virtually everything out there in nature. Virtually everything that nature builds is a fractal. Think of clouds, think of trees, big trunk, smaller limb, another limb, branch, smaller branch, a twig, a smaller twig. Virtually everything in nature is fractal. Yet what humans build comes from Euclidean geometry. What nature builds comes from fractal geometry. And since everything out there is a fractal, we can use chaos games to reproduce those images. We just reproduced the fractal fern. And that's, in fact, what's going on in Silicon Valley, or what has gone on in Silicon Valley. Think of the numbers that you need to produce this image. Right? There were just 4 matrices, 2 translation vectors. There was a probability. About 27, 28 numbers governed this object here. When you go to Microsoft, what's their encyclopedia, Microsoft Encarta, or many of the Encartas, they've got millions of pictures on these CDs in these encyclopedias. How do they store all that data of all these pictures on a single CD? Well, they use data compression. If you click on a fern, chances are you're using a data compression algorithm. Only 28 numbers produce this fern. If you click on Abraham Lincoln, right, he's a pretty good fractal, long stringy hair, beard, wrinkles, wrinkly uniform. Some parts of them are not fractal, but a lot of parts are fractal. You can divide this image up into fractal pieces. Okay? Then very few numbers reproduce that image. You get the fractal image. That's one of the ways they've actually used this in Silicon Valley. Okay, actually, the algorithms have moved over the years. Now they use wavelets more than these compression algorithms, but basically it's the same sort of thing. In any event, you see how we got the fern? You see how the fern came out here? Think of what we've been doing before. We've been looking at these various fractals and seeing what happens when we apply various rules. What happens if we apply rule number 1 to the fern? Remember, rule number 1 was squish more from the bottom than the top. When I apply that to the fractal, I get the top self-similar piece. And what about applying rule number 2 to the fern? Remember, rule number 2 was squish and rotate left. Squish and rotate left. I get the lower left frond of the fern. And what about rule number 3? Remember, rule number 3 was first flip across the vertical axis, and then squish and rotate right. Gotta have some fun. Okay? And I get the lower right frond of the fern. Notice that this curves upward this way, whereas the lower left curved upward the other way. That's why I flipped. What's missing? The stem. How do I get the stem? Rule number 4 says squish almost completely. And there is the fern. Very few numbers give this picture. Okay, now I said that several of my students have gone on to Hollywood, okay, to work in the film industry. Here I am stuck home teaching calculus while all these students are out winning Academy Awards. That's always kind of bothered me. So I decided to get into the game. Here's a movie, okay, which I think will win an Academy Award. How did I make this movie? Each frame of this film is a different fractal. Looked all over Hollywood, but I could only find the fern. How did I make that movie? What am I doing here to make the fern blow in the wind? What rule am I changing? Remember rule number 1, squish, rotate a little bit. I'm just changing that rotation. Okay? So I'm basically just changing one number to produce that animation. Of course, now in the background animations you see in these extraterrestrial movies, they've got lots of ferns and trees, but you can just change one number for each one to make things change. Of course, if you go to Planet X, that's not what happens to ferns, right? What usually happens is these ferns droop. So here's a more accurate animation. How did I make this movie? Notice there's a lot going on here. You see these left-hand fronds are going up and down. If you look at the lower fronds there, they're moving up and down. And if you look at the subfronds of the subfronds, they're moving up and down. A lot's going on there. Okay. What did I do to make this movie? Remember rule number 2, compress and rotate left. I'm just changing one number to make that compression that go up or down. Okay. So I don't know whether the Academy Awards have been announced yet, but I'm pretty sure that one of these movies is going to win. So make sure you pay attention to that. Or if have they been announced yet? They have? Oh, I must have been on traveling name. I don't know. Anyway, the point is that there's lots going on in mathematics, a tremendous amount going on in mathematics. And, well, maybe I'll stop there. Thank you. Okay, and oh, by the way, I have the website here. Yeah, all those applets you saw, Fractal Ena, Fractal Animate, and the Chaos Game are at this website. So have fun. Thanks.